I have a brown apple. Cucumber in this bit too.
Okay, all right, let's get to it. I think few people are gonna be trickling in here in a little bit. So thank you for all being patient and doing a great job finishing your lab today. It took 10 minutes more. So thank you for that. And then I'm going to start a whole new section today, which is proximate composition. We're going to talk about different components within proximate composition, but let's define when we say proximate analysis, what analysis we're really targeting. When we say proximate composition, what do we really mean by that composition? Do you have any thoughts? Do you have any thoughts about what components are we targeting within proximate analysis or composition?
Fat. Moisture. Protein. Carbs.
One more. One more. There are 5. Huh?
That's nice. No.
Ash. All right. So proximate composition is really the main macro kind of components of the food: moisture, protein, fat, carbohydrate. Ash represents the mineral, but all of the inorganic matter, really. And do we know why we call it proximate?
Or it's not exact.
Yes, because it's not exact. It's most of these analyses will give us a crude estimation of these components. So it's an approximation of all of these components. And not only that, they all have to add up to 100. So basically, it's called approximation because if you think about it, I always draw a pie, kind of. So it's kind of like everything needs to add up to 100%. So each proportion contributes to this pie. So you have 1, 2, 3, 4, 5 components, and they all have to add up to 100%. So basically, your components are right there. So moisture, ash, fat, protein, plus total carbohydrates. So the reason I paused about plus total carbohydrate, not because I don't like carbohydrates, but we can determine by specific methods the moisture, total ash, total fat, total protein, but there is not one method that gives me total carbohydrate in a complex food. Carbohydrate proportion is so diverse. You have the dietary fiber, you have the small sugars, you have the starch. There's not one method that will give me total carbohydrates of all of these different components. And I need this to be a total of 100. So it cannot be 102 or 110 or 120. So what I do is I determine percent moisture, ash, fat, protein, subtract from 100, and then get total carbohydrate. So the total carbohydrate in proximate analysis is really a calculated percent. We do not measure it. So out of all of these 5 components, what do we have on the label? What do you see on the label? All out of these 5 components. Fat, protein, total carbohydrate, and that's it. All right. So I have the total fat, total carbohydrates, and total protein. But I don't have ash and moisture. However, all analyses are required for nutrition label. Why? When I want when I want to produce a nutrition label, I have to analyze moisture and ash. Why? I just said it. So I can determine the carbohydrate, which is calculated, and that's what goes in this place on the nutrition label. So total carbohydrate is calculated. Then there is an assay for dietary fiber and there is an assay for sugars, right? Separate from the total carbohydrate measure, which is by subtraction from 100. So that's why when I need to do a nutrition label, I have to analyze all four components so I can get the total carbohydrate. Okay, very good. All right, so in order for me to utilize the data for nutrition label, all the methods have to be official methods of analysis. And official methods are also known as primary methods of analysis, and these are the ones that have been validated by official organizations that validated these tests, like AOCS methods, AOAC methods, AACCI methods. So all of these organizations have validated methods that we can use for the nutrition labeling. So for moisture, oven drying methods such as vacuum oven and forced air draft oven, these are official methods of analysis for a lot of foods. Dry ashing, we will learn about it next week. And then fat, Soxhlet, and Moginer are official methods of analysis, but we do not use them for nutrition label. We actually use GC FAME analysis. Why is that? Because we'll learn about that, I think, Friday. Fernanda will be teaching that section. But, you know, fat or lipids is a term that is loosely defined as anything that is not soluble in water, but soluble in organic solvent. So it contains so many different things. It contains fat-soluble vitamins. It can contain pigments. It can contain so many different components that are not necessarily your triglycerides and such. So with FAME, we can determine the fatty acids and then add glycerol in a molecular formula and calculate the percent fat as total triglycerides. So this is how fat is determined for nutrition labels. So the same FAME method that you did, the only difference is we actually run standards of all fatty acids from C4 to C22 and add them all up, taking into account glycerol, and calculate triglycerides present in your sample. And that's how we report percent fat on the label. So it does not really contain all of the lipid components that would loosely defined as non-soluble in water, but soluble in organic phase, which really your Soxhlet and Moginer can contain other than triglycerides in that fraction. And then protein, we can determine protein either by Kaldal method or the Dumas method. Both are based on nitrogen analysis, and we'll have a whole lecture on that and lab as well. And then total carbohydrate by difference, like I said. Any questions? So total carbohydrate is basically, we, like I said, determine all these four, subtract from 100, we get our total carbohydrate. Okay.
Could I ask a quick question about
Sure.
protein? Because I know we've mentioned that before, they've used things to like increase the protein content by just adding molecules that have nitrogen in them. Would this method be able to identify like, different protein content?
That's exactly how adulteration was not caught, because usually these are the official methods of analysis and they're based on nitrogen content.
Right.
So no,
But if we suspect we hope that it's not adulteration is a common thing. So, but if we suspect adulteration, we need to use non-nitrogen, non-amine based methods for determination. Yeah, good question. All right, so let's look at this. Now we're going to focus on moisture analysis, which is one component of proximity. Moisture content and water activity are interchangeable terms. Thank you. I love the animated sound. Okay. All right. So what about B, Emma? All methods for determining moisture content are based on evaporating moisture and measuring dry matter? No. Which method you did today was not based on that? Carl Fisher, yeah. C, moisture content is an accurate indicator of perishability. Okay, so none of the above. So tell me why moisture content is not an accurate indicator of perishability. Yes, Emma? Marie said you want Marie to answer? Okay, she raised her hand for you.
Because water activity is bioavailable water, which is related to available water for microbes and degradation.
Chemical reactions.
Chemical.
Yes. So water activity is really the water that is active, whether it's active for biological reactions, enzymatic is biological reaction as well, and microbial growth, and chemical reactions such as Maillard reaction, for example. Yeah, so moisture content is really all the water that is not chemically bound within a molecule. Like it's not part of H2O, is not really part of the molecular structure. But water activity is that component of that water content that is available for reactions and growth. So water activity is mostly used alongside moisture content to predict shelf life and perishability by using an isotherm. You love that, don't you? Yes, Emma. You were ahead of me. Hold on. Yes. I needed to read. Yes, yes. So it is definitely an isotherm is a feature that we plot actually, which is a relationship between the moisture content and the water activity, and it gives you this nice kind of S shape, and it gives you something we call monolayer, which is below which you have stable product, and above which you start having different regions where different reactions and microbial growth can happen. So we'll talk about isotherm later. I know you covered it in food chem, but now we'll talk about it in analysis side of things. How do we determine it and how do we read it? Okay. All right, very good. So what is the definition? When you hear moisture analysis, what are you analyzing? Two components. What are they? Just said. And yes. So moisture analysis doesn't mean just measuring the protein content. What you did in the lab today, you did moisture analysis where you determined moisture content and water activity. So that can get confusing, right? You're analyzing moisture content, you're analyzing water activity, and together they're moisture analysis. Okay. We kind of talked about what's the difference between water content and water activity. So water content is the moisture content basically all the water that is not part of a molecule or part of or chemically bound. So the dry matter remains after water is removed. And there is no way we can remove all of the water because some water is bound tightly, not chemically like covalently, but tightly. That's why we call it proximate. We can never get the 100% moisture out. It never happens. So that's why it is an approximate, a crude measure of water, given the fact that the water is bound by hydrogen bonding, dipole interaction, and some components, lactose, for example, is hygroscopic. It's very hard to dry lactose if it's in solution because of its ability to really bind tightly the moisture. That's what hygroscopic is. It just binds so strongly to water. If we want to define water activity, it can also sometimes defined or stated as percent relative humidity. And it's really, this is the definition, it's the partial pressure of water in the atmosphere above the food in relation to the vapor pressure of water, of pure water. So the vapor pressure of pure water, then it's 100. And then of a food product, it's not pure water, so it's always less than 1. So water activity is always in the range of 0 to 1, 1 being the highest, and it's for 100% water. So if you have water, just pure water, water activity would be 1. And 0 doesn't really exist. It would be where you really have all the water is chemically bound and you have nothing that can be in the atmosphere above the sample, which is hardly exists. So now this is going to become a theme. Every time we're going to talk about the analysis of a component, we're going to say, why is it important? Why do we care in food analysis? Why do you care in an industry or in a research lab? Why do we care? Tell me. Yes. Go ahead.
Sorry, shelf life and spoilage instead of it.
Very good. Shelf life. Spoilage. Okay, what else? Yes.
Oh,
Golden. Say, what are you going to say?
I was gonna say texture of the food.
Oh, quality then, huh? So sometimes you really need to have a specific moisture content, so it's not like soggy, it's crisp. Sometimes also for the stability of grains, you don't want to have wheat with a moisture content above 12% during storage. So it's really a characteristic of quality, whether it's for texture or for any other quality parameters. Okay, so very good. So preservation, stability, quality. What else? Anything else you can think of? All right, let's reveal. Sometimes we want to dry or concentrate the sample to a specific moisture content so that it's less volume, less weight, good for transportation, or good just in general. You can sell a concentrated milk rather than the entire whole volume of liquid milk, better for preservation. And sometimes you want to measure to determine if the product meets the standard of identity, and this is very important for milk. So milk has 87% water. If you measure water of milk and it's 89 or 90, that's watered down milk. Okay, we need it for nutrition label. We need the ash and moisture for nutrition label to calculate total carbohydrate. And often we determine the moisture content because when we publish and if we're looking at the compositional differences between different food products, they might be different in water, but we need to take that component out to determine how different they are in what matters in terms of caloric or functionality, how different they are in protein, in fat, in carbohydrate, without the impact of the difference in moisture content. So often moisture content is determined to calculate different components on dry basis. So that helps with comparison across the board, regardless of the differences in moisture content. Okay. So challenges with moisture analysis, like I said, we can never get all the 100% of water out. So that's why it's called proximate. And that has to do with the water structure, layering of water, and how strongly this water is interacting with the different components or the different ingredients. Like if you have, like I said, the example of lactose and how hygroscopic that is. So that makes it really challenging to analyze, but also another component or another parameter that might impact moisture analysis. Have you ever left a drop of water and came back and saw it evaporated? So water, it moves into different stages, liquid to gas state, even not at boiling temperature. So that is the water has mobility, movement into different states, even at atmospheric pressure and temperature. So that's why when we're measuring moisture content, we really need to avoid losses of water during sample prep. So for example, I was telling Kelly, we opened cheddar cheese for amino acid analysis, not amino acid, sorry, AA for mineral analysis. I asked Kelly, you need to get us a fresh sample. That package was not open because the open package could have either made the cheese lose sample and lose moisture to the atmosphere, or if it's a dry product like baby cereal, if you leave it open, you leave the box open, what's going to happen is going to take humidity from the atmosphere, water from the atmosphere is going to get into your sample, and you will overestimate the moisture content because water moves from wetter to drier kind of place. And so a very wet sample might lose moisture to the atmosphere because of the difference in relative humidity between the sample and the atmosphere. And a dry sample can pick up humidity from the atmosphere. So it's very, very important to try to avoid loss or gain of moisture prior to your moisture analysis. Okay. There are almost infinite number of methods to determine moisture content. So the direct moisture content methods it's a long list. Most of them are based on a change in weight by drying, but some are chemical desiccation or a Carl-Fisher titration. These are not drying methods. So we're going to talk about a lot of them, probably all of them. And then the indirect methods. So also there are a number of them. For example, fractometer. So you're measuring total solids. So once you know the total solids, you can determine the total moisture. So it's an indirect method. Or change in density, like the pycnometer is determined based on change in density. Hydrometer, both pycnometer and hydrometer are for liquid samples. NIR, you measure the vibration of the OH functional group. So you can measure moisture content. It's a secondary method of analysis, required calibration. freezing point, this is often done for milk because milk has a specific freezing point. If the freezing point is higher than the standard for milk, you know that you have water in your milk. So measurement of conductivity. So many different methods. It's kind of ridiculous how many methods are out there to determine moisture content. So we're going to talk about that. So for oven drying methods, the simplest form of measuring moisture content is really you heat the sample, evaporate the moisture, and determine the weight before and after. The difference would be the moisture content. And this is what you did in lab and what you will be doing for your lab report, which I forgot to tell you when it's due. Did I? Because you're going to get the data tomorrow, it will be due Friday. The, what is 7th, huh? Yeah. So November the 7th is a Friday, and that's when it will be due. Just, I forgot to mention that. Okay. All right. Distracted. But yeah, so it's very easy to calculate moisture content. Just get the wet weight and the dry weight. That's why you're all gonna come tomorrow and measure the sample weight after drying. And then the relative to the original weight times 100 is your percent moisture. And then you would go, really, moisture content on dry basis. This sounds silly, doesn't it? Moisture content on dry basis. You don't get it.
I don't.
You know, for the longest time, I didn't get it either. But I determined that I learned from the late Ted Labuza that this is very important for isotherm calculation. Because the isotherm calculation is based on moisture content on dry basis. What does it really mean? It just means moisture ratio to dry matter. That's what it means. So in a percentage. So the ratio of the water to dry matter in a sample in a percentage, it's important for isotherm. It has no other relevance or importance anywhere else. So before hearing Ted Labuza, it didn't make any sense to me, moisture content on dry basis, but then I understood, and now I'm telling you what I learned. So that's where it's needed, and that's where you're going to, why you're going to quantify on dry basis, although you're not going to determine isotherm. It used to be component of the lab, but we removed it. It was a little bit tedious process. So it's no longer part of the lab, but that's why I just want you to know the relevance of it. And like I said, it's just a mere ratio of water to solid in a food product in a percentage format. So when you do percentage, do you ever expect that a component will be over 100%? Doesn't make sense, yeah? But moisture content on dry basis can be over 100%. How can you even guess where moisture content on dry basis can be over 100%? Yes, when there is more moisture than solids in a sample. And processed cheese, which used to be one of the samples for groups when we had more than 3 groups, sometimes have over 50% moisture content. So when we determine moisture content on dry basis for processed cheese, it will come out as over 100. Again, this is just to illustrate that it's just a mere ratio of solids or water to solids. Okay. Good. So consideration. There are samples. If we are using ovens, we have limitations when you are working with something that is liquid, like milk. So milk if you try to put milk in the forced draft oven that you use today, what's gonna happen? It's about 100 degrees. What's gonna happen? The milk in your pan. Start boiling, and what does it happen? It might splatter out, right? We cannot put just milk right there. What we do in this situation is we pre-dry it a little bit before putting it in the oven. So we weigh the sample so that we have the weight of the wet sample. We put it in a water bath or a steam bath, and then we let it evaporate, like it becomes kind of a concentrated milk, and then put it in the oven. This is part of the official methods of analysis for milk. Other times at high temperature, we get decomposition of food constituents. Can you give me an example of a chemical reaction which is a degradation reaction? Emma, you tell me your favorite. So Maillard reaction is actually a condensation reaction. So what happens is when protein reacts with your reducing sugar, you lose a molecule of water. With every bond formed, a molecule of water is lost. Then that molecule of water that was chemically bound is now lost. Then you overestimate moisture content. So that's a chemical reaction where you overestimate moisture content because bound water is lost, is evaporated. Okay, another chemical reaction is simply burning. So carbohydrate can burn, and then with burning, you also lose water. Water comes out from being molecularly bound. So that also causes overestimation. Loss of volatiles. So you have volatiles like flavor components are volatile. Other components could be volatile that will just simply volatilize. And then that will cause overestimation of water. Because you're simply measuring the difference in weight. So if things volatilized, other than the actual water that you had there, that you overestimate water. So chemical reaction can cause underestimation as well. So one example of a chemical reaction that causes underestimation is lipid oxidation. Why? Because lipid oxidation takes up oxygen from the atmosphere. Now the oxygen weight is part of your dry matter. So then you underestimate. So your dry matter will have a little bit more weight than when you don't have lipid oxidation. So then you have an underestimation. So these are examples of decomposition of food constituents that will lead to over or underestimation. So temperature control is important in this case to avoid decomposition as much as you can. So you want to make sure your temperature doesn't fluctuate, doesn't become colder, then you will not evaporate all the water, or too hot to cause more of the decomposition. So it's important sometimes to have covers or to use glass wool so you can avoid some of, especially you did that in the first draft oven, right? Because there's a lot of circulation of air. So powder samples can just get blown off from the pan. So we put this glass wool, or more fancy, we have like covers that have holes to allow evaporation of water, which we don't have. So we use glass wool. Sometimes if you are trying to evaporate water, and then depending on the composition of sample, you might have a crust on the top formed. And if a crust is formed, water gets trapped. So you won't get evaporation of water. So there is the sand pan technique. So from the name, what are we doing with the sand? Huh? Well, we mix it with the sample. so that we kind of break any potential for crust layer formation. So, but you need to use like clean sand that does not react or have any component that cause decomposition at high temperature. So really reagent grade sand. Okay, so with that said, there are a lot of sources of error. Particle size is really important. If you have cheese, for example, the cheese group, what did you do? You grade your sample. You graded it. So you want to reduce the particle size so that you can have higher surface area for evaporation. Some errors cannot avoid if you have volatiles. They're going to contribute to inaccuracy. We talked about high temperatures, burning issues, lipid oxidation, hygroscopic, like high lactose, for example, a carbohydrate alteration by Maillard reaction or even burning, the crust formation, splattering of liquid sample, improper storage that might cause dehydration or hydration. So all of these are a lot of potential sources of error. We try to reduce as much as we can and control. But again, that's why it's proximate, because no matter what we do, there's always going to be error that we cannot control 100%. All right, so now we're going to talk about drying ovens, which you've seen today in the lab. Forced draft oven, this method is AOAC approved, AACCI approved for many different foods. So you saw the oven, so you put your sample and we have circulating air. So you have a constant flow and consistent temperature across the oven. So wherever you put your sample, the air draft in there is making sure that the temperature is consistent throughout the oven. So that's one of its advantages, is that no matter where you put your sample, it's not going to be more hot in one area and less hot in another. It's very simple. You weigh, you put it in, leave it 24 hours, take it out, put it in desiccator to cool, and measure. Very, very simple. However, the errors, the common errors is you lose volatile compounds, you can get Maillard reaction happening or burning, so you have a little bit of an overestimation. The splattering, which we deal with by concentrating before putting in the oven, and the powders, we prevent that by the glass wool or a cover. Vacuum oven has advantages over the forced draft oven because we can dry at lower temperature. So when you have vacuum, the boiling temperature is reduced of water, so it evaporates at lower temperature. So by doing that, you avoid burning and potentially Maillard reaction. But you still have some disadvantages. Still, volatiles might evaporate, causing overestimation. And in the vacuum oven, you don't have uniform distribution of heat. Often the CV, the coefficient of variation for replication, is higher in the vacuum oven than in your forced draft oven. So this is something to keep an eye out on when you look at your data, comparing vacuum to forced draft. And one thing you probably saw it today in the lab, that we need to make sure that the water trap, which we use a desiccant, the desiccant is not saturated with water. So the reason we have a water trap, or called cold finger, I don't know why they call it cold finger, but that's what it is that when moisture is sucked out of the oven, it doesn't go to the vacuum pump and ruin it. So it just collects the moisture between the oven and the pump. And we use desiccant And the desiccant change color to purple when it's saturated. So we want to make sure that we dry the desiccant often so that it's always looking blue, not purple. You also saw the microwave oven. That's the last thing I'm going to talk about. So the microwave oven is quick method of analysis, but it's not an official method of analysis for many types of food, only for limited number of food, and it's not suitable for the foods with high carbohydrate, like baby cereal, for example. Did you see it burn? Did it burn for you? It didn't? It worked for you? Well, you might get burning of high carbohydrate. You might then get overestimation. It's really good for cheese. You'll see that you have good, accurate results for cheese samples. But the idea is to make sure that your sample is uniform, centered. So a very thin layer, uniform layer when you put it in the microwave. And it's very quick, 4 to 8 minutes. And the pilot plan using it as quality control, quick measure for moisture content. All right, I'm gonna stop here. I will see you guys on Monday. Fernanda will be here Friday, talk about fat analysis. All right.
What about if
Yeah.
dry something like that?